Schrödinger's cat, a mind-bending paradox that challenges reality itself. Schrödinger's cat is one of the most famous, mind-bending, and controversial thought experiments in the history of science. It challenges our understanding of reality, observation, and the very nature of existence itself. The paradox was first introduced in 1935 by Erwin Schrödinger, an Austrian physicist who was deeply puzzled by the strange implications of quantum mechanics, the science that governs the smallest particles in the universe. What he proposed wasn't just a bizarre scientific riddle, it was a fundamental question that still shakes the foundations of physics and philosophy today. Does reality exist in a definite state before we observe it, or is it merely a collection of possibilities waiting to be seen? To understand this paradox, let's dive deep into the world of quantum mechanics, where the rules of everyday life fall apart and where particles behave in ways that seem completely impossible in our normal experience. Imagine you are in a physics laboratory, standing in front of a completely sealed box. Inside the box is a cat, along with a carefully designed setup. A radioactive atom that has a 50% chance of decaying within an hour and a 50% chance of remaining stable. A Geiger counter, a radiation detector that will trigger if the atom decays. A mechanism connected to the Geiger counter, designed to release a deadly poison into the box if the detector senses radiation. If the atom decays, the Geiger counter detects it, triggering the mechanism and releasing the poison, killing the cat. If the atom does not decay, the mechanism does nothing and the cat remains alive. Now, here's where things get truly bizarre. According to classical physics, we might expect the cat to be either dead or alive at any given moment, just as a coin that has been flipped is either heads or tails, even before we check. But quantum physics tells a different story. At the subatomic level, particles do not behave in a predictable, well-defined manner. Instead, they exist in a state of superposition, a mysterious condition where they can be in multiple states at once until they are measured. This means that until we open the box and check, the radioactive atom is in a superposition of decayed and undecayed states at the same time. And since the cat's fate is tied to the atom, the cat itself must also exist in a superposition of being both dead and alive at the same time. It is only when we open the box and observe the cat that reality chooses a single outcome. Either the cat is dead or it is alive. But before we look, it is both at once. At this point, we must stop and ask ourselves, can something really exist in two contradictory states at the same time? Is reality itself undefined until we observe it? This is the heart of Schrödinger's cat paradox, a direct challenge to our understanding of reality. It suggests that, in the quantum world, objects do not have definite states until they are observed. But if reality depends on observation, who or what is the ultimate observer? If we never open the box, does the cat remain in limbo forever, caught in a state of being both dead and alive? And what does this mean for the universe itself? If the moon is behind a cloud, does it still exist in a definite position, or does it, too, exist in a state of probability until someone looks at it? Schrödinger himself devised this thought experiment as a way to highlight the absurdity of quantum mechanics. He wasn't necessarily arguing that a cat could literally be both alive and dead. He was pointing out that the way we interpret quantum theory doesn't make sense when applied to everyday objects. But this leads to another unsettling question. If quantum rules apply to atoms and subatomic particles, then why wouldn't they apply to larger objects like cats, people, or planets? One possible answer comes from a radical idea known as the many worlds interpretation. According to this theory, every time a quantum event happens, every time a particle takes on one state or another, the universe splits into two separate realities. In one universe, the atom decays, the poison is released, and the cat dies. In another universe, the atom does not decay, the poison is never released, and the cat remains alive. This means that every possible outcome happens, but in a separate, parallel universe. If this is true, then we are constantly creating infinite versions of reality, branching out in countless directions, each containing a different version of ourselves, living different lives. Perhaps in another universe, you made a different choice today. Perhaps in another universe, history took an entirely different path. Perhaps in another universe, another version of you is reading this explanation, wondering the same things. But if multiple realities exist, then what determines which one we experience? If every possibility is real somewhere, then what makes this version of reality feel so unique and definite? Schrödinger's cat isn't just a strange thought experiment, it raises questions that challenge the very fabric of existence. It forces us to rethink what we mean by reality, and to ask whether the world around us is solid and objective or merely a shifting landscape of probabilities waiting to be observed. Could it be that everything we experience, every sound, every color, every touch, isn't really there in a definite form until our minds interact with it? If observation is what makes things real, then what was the universe like before there were observers? And if reality depends on an observer, then could it be that consciousness itself plays a role in shaping the universe? These are not just abstract ideas for physicists to ponder in labs, these are the kinds of questions that shake the very foundation of our understanding of life, reality, and existence. If a cat can exist in two states at once until someone looks, then perhaps all of reality is the same way. And if everything exists in a superposition of possibilities until it is observed, then what does that say about the nature of our own choices, our own lives, and the world we think we know? Schrödinger's cat is more than a paradox, it is a doorway into the deepest mysteries of the universe. And maybe, just maybe, reality itself is nothing more than a dream, a shadow of possibilities waiting for us to open the box and look inside. The simulation paradox is one of the most fascinating and unsettling ideas in modern science and philosophy. It raises a question so profound that it challenges the very nature of reality itself. What if everything you know, your thoughts, your memories, the world around you, is nothing more than an incredibly advanced simulation? What if the universe itself is not what it appears to be, but instead a vast and sophisticated artificial construct, designed to mimic reality so perfectly that no one inside it could ever tell the difference? At first, this may sound like science fiction, but some of the world's leading physicists, philosophers, and even technology pioneers take this idea very seriously. The core of the paradox is simple yet disturbing. If a civilization ever becomes advanced enough to create fully immersive, conscious simulations, then how can we be sure we aren't already inside one? If this kind of technology is possible, then statistically speaking, it is far more likely that we are inside a simulation than in the real world. To understand why, imagine a future civilization, a species millions or even billions of years more advanced than us. Their technology is so sophisticated that they have computers capable of simulating entire universes, complete with living, thinking beings who believe they are real. These simulated beings have no way of knowing that their world is artificial, because to them, it behaves exactly like a real universe would. If this civilization can create one such simulation, then there's no reason they wouldn't create millions, or even trillions of them. Now, consider the numbers. If there is only one base reality, but countless simulated realities, then what are the chances that we are in the single real universe rather than one of the many artificial ones? The logic is unsettling. The probability suggests we are far more likely to be inside a simulation than in a physical universe. This argument was made famous by philosopher Nick Bostrom, whose simulation hypothesis suggests that advanced civilizations would inevitably reach a point where they could create simulations so detailed that the simulated beings would be completely unaware of their artificial nature. But why would a civilization create these simulations in the first place? There are many possible reasons. Perhaps they are scientific experiments, designed to study the past or explore possible futures. Perhaps they are forms of entertainment, much like we play video games today. Or perhaps they are used to train artificial intelligence by allowing it to develop in a controlled, simulated environment. If this is true, then what proof do we have? How would we ever be able to detect a simulation from the inside? Some scientists believe that the laws of physics themselves contain clues that reality might not be what it seems. One such clue is the Planck length, which is the smallest possible unit of space in our universe. Nothing can exist on a smaller scale than this. But if our reality were truly infinite, why would there be a smallest unit at all? This suggests that the universe might be pixelated, much like the resolution of a digital screen, meaning that space itself is not continuous but is instead composed of tiny, indivisible units. Another clue lies in the speed of light, which appears to be an absolute limit. No information can travel faster than it. But why would the universe impose such a hard speed limit? Some physicists speculate that this could be because our reality has a processing limit, just like a computer simulation. If the simulation needs to calculate every event in real time, then limiting the speed of information transfer might be necessary to maintain coherence within the system. Then there is the mystery of quantum mechanics. Scientists have discovered that at the smallest scales, Particles do not exist in a definite state until they are observed. Before they are measured, they exist in a probability wave, where they occupy multiple states at once. But why would reality behave this way? One possible explanation is that, in a simulation, resources are only used when they are needed, just like how a video game only renders the part of the world that the player is looking at. Could it be that the universe only renders reality when we observe it, to save computational power? If we are in a simulation, then the next question is even more unsettling. What happens if we find out? If the simulation is designed to be undetectable, would the creators shut it down if we got too close to the truth? Or perhaps we are meant to discover it. Maybe the simulation is a test, designed to see how long it takes for intelligent beings to figure out that they are inside an artificial world. If we could somehow hack into the simulation, would we be able to change the rules? Could we alter reality, rewrite physics, or even escape into whatever exists outside of it? And if this world is a simulation, then who, or what, created it? Could it be an ancient, hyper-advanced alien civilization running experiments? Could it be our own descendants from the distant future, creating simulations to study the past? Could it even be something beyond our comprehension, an intelligence so vast that we are no more aware of it than a character in a video game is aware of the person playing it? And if they created us, then what created them? Could they, too, be inside another simulation, part of an endless chain of realities, one inside another? If we are inside a simulation, does that change the way we should live our lives? If reality is artificial, does it make our experiences less meaningful? Or does it simply mean that the nature of reality is different from what we assumed? If we feel love, joy, pain, wonder, then those feelings are real to us, regardless of what lies beneath the surface. Perhaps, in the grand scheme of things, it doesn't matter whether our world is real or simulated. Perhaps what matters is how we experience it. If we are inside a simulation, then maybe this world is just as real as any other. Or maybe reality itself is just a dream waiting to be awakened. But the question still lingers, haunting the deepest corners of human thought. If we are in a simulation, then who, or what, is watching us? The celestial teapot, also known as Russell's teapot, is one of the most powerful and thought-provoking thought experiments in philosophy. At its core, this paradox challenges a fundamental question: who is responsible for proving a claim? The one making it or the one rejecting it? Now, let's go on a journey into the depths of space. Imagine that somewhere in our solar system, far beyond the reach of any telescope, there exists a tiny porcelain teapot orbiting the sun. It is too small to be detected by any modern instruments, and no spacecraft has ever encountered it. Now, what if someone came to you and confidently declared, "This teapot exists, and unless you can prove me wrong, you should believe in it"? What would you do? You might say, "That sounds ridiculous. There is no reason to believe in this teapot." But then, the person insists, "Can you prove it doesn't exist?" This is where the problem arises. In everyday life, we don't assume something is true simply because we can't disprove it. We don't believe in invisible pink unicorns, flying spaghetti monsters, or magical fairies in our gardens just because we have no proof that they don't exist. And yet, Russell's teapot forces us to ask, if something cannot be proven false, does that make it true? What happens if we reverse the way we think about belief? What if we treated every unproven claim as true until evidence suggested otherwise? If we applied this logic, then we would have to believe in every possible fantasy, conspiracy, and superstition, because we wouldn't be able to disprove them all. And that's exactly what makes Russell's teapot so important. It exposes a common logical fallacy, the idea that a belief should be accepted unless it is disproven. But in reality, the burden of proof always lies with the person making the claim. Imagine a courtroom. A person is accused of a crime. There is no evidence against them, no witnesses, no fingerprints, nothing. The prosecution stands up and says, "You cannot prove you didn't commit this crime, so we must assume you are guilty." Would this be a fair trial? Of course not. In a just legal system, we operate under the principle that a person is innocent until proven guilty, not guilty until proven innocent. The prosecution must provide evidence. Otherwise, anyone could accuse anyone else of anything, and simply demand, "Prove me wrong." Now, let's take this principle and apply it to everyday beliefs. If someone claims that ghosts are real, should we believe them until someone proves ghosts don't exist? If someone insists that aliens are secretly controlling our government, do we assume it's true because no one can disprove it? If a person declares that there is an invisible dragon in their garage, Do we accept it as real just because there's no way to show it isn't there? Russell's teapot reveals the danger of this kind of reasoning. If we start assuming things are true simply because they haven't been disproven, then there is no limit to what we could be forced to believe. This is where the burden of proof comes into play. In science, law, and rational debate, the burden of proof always falls on the one making the claim. It is never the responsibility of others to disprove something that lacks evidence. If someone says, a celestial teapot is orbiting the sun, it is their responsibility to provide evidence. It is not the responsibility of others to disprove it. Russell originally introduced this analogy as a critique of blind faith and religious beliefs. He argued that supernatural claims often escape scrutiny because they are framed in a way that makes them difficult, if not impossible, to disprove. Many religions, for example, assert the existence of deities, spirits, and supernatural forces, and when skeptics demand evidence, they are often told, you can't prove that these things don't exist. But Russell's teapot shows why this reasoning is flawed. The mere fact that something cannot be disproven does not make it worthy of belief. If we accepted this logic, then we would have to believe in an infinite number of unproven things. A giant invisible cat living on Pluto. A secret underground civilization beneath Antarctica. A race of time-traveling lizard people controlling the world. If we had to accept every unproven idea just because we couldn't disprove it, we would be overwhelmed by an endless flood of absurdities. This is why extraordinary claims require extraordinary evidence. The more unbelievable or unlikely a claim is, the stronger the evidence must be before we take it seriously. If someone claims they own a car, we might believe them without much proof. Cars are common, and their claim is reasonable. But if someone claims they own a pet unicorn, suddenly, we need a lot more evidence before we believe them. And if they tell us, you can't prove I don't own a unicorn, so you must believe me, we recognize the absurdity of their argument. Russell's teapot highlights a fundamental principle of logic. If you are making a claim, it is your responsibility to provide evidence, not someone else's job to prove you wrong. And yet, even today, this principle is often ignored. From pseudoscience to conspiracy theories, from religious dogma to misinformation, many claims rely on shifting the burden of proof, placing the responsibility of disproving a claim onto skeptics instead of providing real evidence. The next time someone makes an extraordinary claim, remember the celestial teapot. If they cannot provide evidence, then their claim is no more believable than a tiny, undetectable porcelain teapot floating through space. And if we start believing things just because we can't disprove them, then what stops us from believing in everything? The ship of Theseus paradox is one of the most fascinating and mind-bending thought experiments in philosophy. It doesn't just question how things change over time, it forces us to confront the very nature of identity, continuity, and existence itself. It asks a deceptively simple yet deeply unsettling question. If something changes gradually over time, at what point does it stop being what it once was? Now, imagine for a moment a legendary ship, the mighty vessel of the Greek hero Theseus. This ship has sailed across vast oceans, battled fierce storms, and become an enduring symbol of power and legacy. People revere it, preserve it, and pass down its stories for generations. But time is relentless. Decay is inevitable. The ship's wooden planks begin to rot. The mast starts to crack. The sails become worn and tattered. To keep the legendary ship afloat, the crew gradually replaces its failing parts. First, a few planks. Then, the mast. Then the ropes, the nails, the sails. Over time, this process continues until, at some point, not a single original piece remains. Yet, throughout this entire process, it is still called the ship of Theseus. It never stopped sailing. It never ceased to be Theseus's ship. But now, stop and think. If every part of the ship has been replaced, is it still the same ship? If identity is tied to its physical components, then the original ship of Theseus no longer exists. But if identity is based on continuity and function, then it has remained Theseus's ship all along. Now, here's where things get even more complicated. Imagine a skilled carpenter had been collecting all the discarded planks, sails, and beams from the original ship. Over time, he carefully rebuilds the ship using only its original materials. Now, we have two ships. The first ship, which has been gradually restored with new materials. The second ship, built entirely from the original, discarded pieces. So here's the question. Which one is the true ship of Theseus? If identity is tied to physical components, then the reconstructed ship, the one made from the original materials, is the real one. But if identity is about continuity, the history and function of an object, then the ship that never stopped sailing is the true ship of Theseus. But what if this paradox isn't just about a ship? What if it's about you? Every 7 to 10 years, nearly every cell in your body is replaced. The physical you that existed a decade ago is completely gone. Your skin has shed. Your bones have regenerated. Your hair and nails have entirely grown anew. And yet, you still feel like the same person. So, if your body has been completely rebuilt, are you still the same you that existed 10 years ago? And it doesn't stop there. It's not just your body that changes, your mind does, too. Your beliefs shift. Your memories fade or become distorted. Your personality evolves. Your fears, ambitions, and desires transform over time. So if every part of you, both physically and mentally, has changed, what remains constant? What is the real you? Think about your childhood self. That version of you had different dreams, different fears, and a completely different understanding of the world. And yet, you still consider that person to be you. But if nearly everything has changed, what connects the past you to the present you? This paradox isn't just about individuals, it applies to everything around us. A country, if its borders, government, and people change over centuries, is it still the same nation? A language, if its words and grammar evolve over time, is it still the same language? A religion or philosophy, if its beliefs shift over time, does it still remain true to its origins? A company, if it replaces all its employees, its CEO, its branding, and even its products, does it remain the same company, or is it something entirely different? These questions force us to face an uncomfortable truth. Identity is not as fixed as we like to believe. We like to think of ourselves, and the world around us, as stable, unchanging entities. But in reality, everything is constantly in motion. So maybe the real question isn't whether something is still the same after change. Maybe identity isn't something rigid, it's something fluid. It's something that flows like a river rather than standing still like a statue. The ship of Theseus paradox forces us to rethink who we are, how we change, and what truly defines us. If every part of your body has changed, every thought in your mind has evolved, every belief you once held has shifted, are you still the same person you were in the past? Or are you just the latest version of yourself? The arrow paradox, proposed by the ancient Greek philosopher Zeno of Elea, is one of the most mind-bending thought experiments in history. It doesn't just question motion, it challenges our entire understanding of time, reality, and existence itself. It forces us to ask, if we break everything down into individual moments, does motion truly exist? Imagine an arrow soaring through the air, released from a bow, flying toward its target. You watch it move smoothly, cutting through the air in one continuous motion. But if we analyze this movement from a different perspective, we encounter a paradox that shakes the very foundation of how we perceive motion. Now, let's freeze time for an instant. At any given moment, the arrow is not actually moving. It occupies a specific position in space, completely still. It is not advancing, not retreating. It is simply there, at that exact location, at that precise moment. If we break time down into an infinite number of these frozen moments, then at every single one of those moments, the arrow is motionless. But here's the question. If, at every individual instant, the arrow is not moving, then how does it ever actually travel from one point to another? Think of time as a sequence of photographs, a series of still frames capturing each moment. Imagine a high-speed camera that records the arrow's flight at millions of frames per second. If we analyze these frames one by one, in each image, the arrow appears frozen in place. It occupies a specific point in space, completely motionless. But if motion is just a collection of still images, how do these individual, unmoving frames add up to create continuous movement? This brings us to a disturbing conclusion. If the arrow is at rest in every individual moment, how can motion emerge when we combine all those moments together? This paradox raises a profound issue. If motion is real, it should exist in every instant of time. But if motion does not exist in any individual instant, how can it exist at all? At no single moment is the arrow actually moving. And if there is no motion in any moment, then how can motion exist when you add all those moments together? This paradox forces us to question the nature of time itself. Is time truly continuous, flowing like a river? Or is time actually made up of separate, disconnected moments, like the frames of a film reel? If time consists of infinitely many still moments, and motion does not exist in any of them individually, then how does movement even happen? If we press pause on the universe, everything freezes in place. Now, when we press play again, what actually causes the transition from one moment to the next? Are we truly moving, or are we just experiencing the illusion of motion? For over 2,000 years, Zeno's paradox puzzled philosophers, mathematicians, and scientists. It seemed to suggest that motion was either an illusion or something beyond our understanding. It wasn't until the development of calculus, pioneered by Isaac Newton and Gottfried Wilhelm Leibniz, that we found a mathematical framework to describe motion. Calculus introduced the concept of limits, which allowed us to calculate velocity and acceleration in a way that made sense, even when dealing with infinitely small divisions of time. In simple terms, calculus says, instead of looking at motion as a collection of still moments, we look at the rate of change over an interval of time. This rate of change, called a derivative, explains how position evolves, even when broken into infinitely small steps. Thanks to calculus, we now have precise equations that describe the motion of everything from arrows to planets orbiting the sun. And yet, Zeno's paradox still lingers in the background, challenging the way we think about time itself. Even though calculus provided a way to mathematically describe motion, it didn't completely erase the mystery of Zeno's paradox. The fundamental question still remains. If time is made up of an infinite number of still moments, and if motion does not exist in any of them individually, then how does motion emerge? Is movement a physical phenomenon, or is it something our minds create to make sense of reality? If motion is an illusion, what does that say about our experience of the world? Modern physics, particularly in quantum mechanics, adds another layer of mystery. On the smallest scales, particles don't move smoothly. They jump from one state to another in discrete, unpredictable ways. This quantum behavior eerily mirrors Zeno's paradox, suggesting that at the deepest level of reality, movement may not be continuous at all. So what does this all mean? If motion is just an illusion created by how we perceive time, if every moment is static and disconnected from the next, then are we truly moving at all? Or are we simply experiencing the illusion of movement in a motionless universe? The grandfather paradox is one of the biggest dilemmas in the concept of time travel. Imagine a simple scenario. One day, you successfully travel back in time and meet your grandfather before your father is born. However, whether by accident or on purpose, you end up killing him. Now, things get complicated. If your grandfather dies, your father is never born. And if your father is never born, you cannot exist. But here's the paradox. If you were never born, then how did you travel back in time to kill your grandfather? This creates a logical contradiction, one that has baffled physicists and philosophers for decades. Some argue that time is a single, unchangeable timeline, meaning that any attempt to alter the past is inherently impossible. Even if you tried to kill your grandfather, something would inevitably stop you. Maybe your gun misfires, maybe you change your mind at the last second, or maybe circumstances beyond your control prevent it from happening. This idea is known as the consistency principle, which suggests that the universe does not allow paradoxes. The past is already determined, and nothing you do can change it. But there's another possibility, one that leads us into the realm of parallel realities. According to this theory, every decision creates a new timeline. If you go back and kill your grandfather, you don't erase yourself from existence. Instead, you create an alternate reality, a new branch of time where you were never born. However, in your original timeline, nothing changes. You were still born, traveled back in time, and created a different version of history. This idea forms the foundation of the many worlds interpretation, which suggests that every possible event spawns a new parallel universe. But what if time is truly malleable? If it is possible to change the past, then time travel would not just be about observing history, it would be about rewriting it. But this leads to an even deeper paradox. If the person who altered history no longer exists as a result of their actions, then who made the change in the first place? Perhaps time is more complex than we think. Maybe when we travel to the past, we aren't interacting with the actual past, but rather a reflection of it, something separate from our own reality. Or maybe instead of changing the past, we are simply creating new versions of it. Either way, the grandfather paradox remains one of the greatest unresolved mysteries of time travel, not just in science fiction, but in real-world physics as well. Whether time is fixed, changeable, or capable of branching into infinite possibilities, one thing is certain: if time travel is ever proven possible, this paradox will be one of the biggest puzzles we'll have to solve.